Hello. So today we're going to talk about two topics. So topic one, we'll talk about three different ways of changing magnetic flux. So this is magnetic flux. Okay, so from the previous lectures, we know phi b is magnetic flux, which is defined as B times A, right? And then we say this is the perpendicular one, and that's equal to the BA times cosine theta, right? So the maximum case is the following, right? So if you have the area, okay, and then you have magnetic flux that's going through, okay. Just a review, okay? So your B is going through, and that's the area, right? So we usually look at the line that's perpendicular to the face of the area, right? And then check the angle between this line, right? This line here, and the B, right? So the theta is between B and the line. Okay? Right. So when we say this B is perpendicular, right? Looking for to A, we're talking about the areas, this is the area's face. When we say this perpendicular, it's perpendicular to the face of the area, okay? All right, so what are the different way of changing phi b, right? So one way to change it, the first way is to change b, right? So if I make b right now, let's say b is equal to 1 Tesla, right? So if I go from b, let's say b1, and now become b2 is equal to 2 Tesla, right? Within the delta t of 1 second. Then, you see that the phi, right? So the phi b, so delta phi, I'm going to drop the b here, will be equal to the phi 2 minus phi 1, which is then equal to b2 minus b1, and then a. For cosine theta, in this case, theta is equal to 0 degree. So this is cosine 0 degree, right? So that's equal to 1. So then that will be the differences that you can calculate. So that's one way. B, so you can change the area, right? So let's say if this wire can actually shrink and expand, right? So if you can change the area, so B is changing the area, right? So you can change the area by making this wire bigger. How do you do that? That's a separate question, right? So you can make the area bigger, or you can make it smaller, right? So let's say now the delta phi would then be equal to, right, phi2 minus phi1, and B is constant. So in this case, B is constant, but we know A2 is increasing. So A2 now is bigger, right? Is equal to 2 meters squared. And original A was 1 meter squared. A was equal to 1 meter squared. So then A2 minus A1, right? And cosine 0 degree, okay? So then you can do that. And C is you can changing the angle, right? You can change the angle, changing theta, okay? So then you can say right now theta is equal to theta 1 is equal to 0 degree, okay? And let's say theta 2, right? So sometime later this change. So let's say if we change this angle a little bit, so we'll draw that to what color? So red color, right? So let's say now this is the axis, right? And this guy is rotating. So he rotated this position instead. Right. Okay, so now the perpendicular one of the area is going this way now. Right, this is the line, and the B still in the same direction. So now you have a theta right there. Let's say theta is equal to 30 degrees or 60 degrees, for example, 60 degrees. Okay, so now you have this delta phi will be equal to BA, and then you have cosine 60 minus cosine 0 degree. So then this one here will be 1/2 minus 1, so which is equal to minus 1/2. Okay, so your flux will be reducing. Okay, all right. So that's the flux changes. Now we're going to apply that to a problem here. Okay, and this problem we have dealt with that before. So basically, if you have a situation like you have a U-shaped conductor, okay? So U-shaped conductor. And then you also have a rod. You also have a rod sitting on it. So this is also a metal rod that's sitting on it. And so this is having contact right there. So there's a little rod, okay? So this is a moving rod. Moving rod, okay? And then your magnetic field is everywhere out of page. Everywhere is out of page. So everywhere is out of page, so everywhere. Just drawing the B field, right? This is the B field everywhere. Everywhere. Too many to draw. Okay. Right? You get the idea, right? So everywhere, okay? Constant B, and it's coming out of page, right? This is out of page. Okay. So now let's say if we are pulling this rod with a velocity v going this way. So the question is, what is the induced epsilon? So this is induced, right? So we're going to use the Farady's law of induction, right? Farady's law of induction to derive that. Okay, so remember this is equal to delta phi b. There's a negative sign, but we're going to drop that negative sign for now. Delta phi b delta t. Okay, this is the b. There was a negative sign for Lorentz law, right? So that's equal to. So what's phi b here? The phi b is equal to. So A is this area right there, right? So let me just. This is currently that's the A right now. Okay, this is the A. And then your B is out of page. So they are 90 degrees in this, right? But then the line perpendicular to the face and the B is 0 degree, right? So that's all we care, is the B times A and then cosine 0. So that's equal to 1. But we got this, right? So that's original, that's B1. That's equal to that. And later, sometime later, okay? Sometime later, let's say this one now move it to here now. Right, this move to here. Okay, so delta t time later, this one here move v times delta t. Okay, so he moved this much. So the area has increased now. We know now the a let's call that a prime. Okay, let's just call that phi b. And a prime now is equal to the this length plus that. So delta a, right? It's called that delta a is a prime minus regional A, right? And that's equal to, and this length here, we're going to call this one here, call that L, right? So this length here, we're going to call that L. So it's L times the distance here, which is V delta T, right? Okay, so that's the delta A that you have is this. All right, so now we can just calculate the delta phi now, which is equal to the phi prime minus original phi. Right, I'm dropping the B here. So that's equal to B, right? A prime minus A, right? Okay. So B doesn't change. So that's equal to B times delta A, which is that one there. Okay. So then that's equal to B L V delta T. All right. So now we're going to put this one here into here now. Change the color a little bit here again. Okay, so then this is equal to, So delta T is going to cancel. That's equal to the BLV. Okay, and that's what we want to see is what kind of induced. So this is induced EMF. So EMF is a voltage difference or electric potential difference, right? So you will induce a voltage in this wire here, okay? And now, since we are increasing the flux, so we need to decrease it, right, by having a current. So the current will have to go clockwise, okay? I'll show you why later. So this is an induced current, right? Have to go that way. Induced current have to go that way. So you get your right hand out. So induced current is going this way. So then you have an induced magnetic field will be going into the page, right? Into the page in the original. So B original, it's out of page. Okay? But the B induced, it's into the page. Okay? So then you can see because the phi is increasing, right? So we know phi is increasing. See that? Phi is increasing. So the Lorentz law, right, says that if you are increasing, then I need to try to reduce you. So then he will induce a B by induce a current, which is due to the induced EMF, so that you have this induced, right? Induced everywhere, right? Everywhere induced B. This is B induced. Okay? So that's what this will do when you have this induced EMF. It would create this induced current, and that will create the induced magnetic field. And then that would then slow down the increase of the flux. Okay? So that's all we have for the day. And hopefully you are learning something interesting. And we'll see you until next time.